Okay, so let's
¿Cómo le apuntas aquí?
let's get started so that the people that it's connected to the channel are in time. So we continue with the session, and now Corina Solis is going to tell us about radiocarbon applications here at the LEMA laboratory. Okay.
No, apunta.
¿No es al revés?
No sé.
Aquí. Acá. No funciona.
No tenemos que prender. Bueno, es mi turno entonces de... Si quieren...
Más que pones el brazo ahí, se hace una
Oye, pero no apunta. Ah, sí, ya.
Tienen que apagar. ¿Listo? Bueno, ahora sí es mi turno para platicarles de lo que hemos hecho en el LEMA en los últimos 5 años, desde que se instaló nuestro laboratorio. I'm sorry, I have to change. Well, in this occasion I will talk about the things that we have been doing in our laboratory, the National Laboratory of Mass Spectrometry, with accelerators, accelerator mass spectrometry. Well, I will talk a little bit about the installation of our laboratory. Again, you will hear a little bit of the basic of the radiocarbon dating, some sample preparation, basically also that we use here in our lab. How we do the carbon analysis, the carbon-14 analysis, and I will talk about several applications very briefly. In the next conferences, you will hear more in detail of what we are doing, several projects that we are developing right now. Well, I will talk about archaeological applications, also radiocarbon dating in art, environmental applications, and hydrological applications. Well, our laboratory started with the support of the National University of Mexico, the Institute of Physics, and CONACYT, which is our National Science Foundation, CONACYT. And it opened in 2013, and LEMA is considered a laboratory for research, teaching, and support for interdisciplinary projects. Here we have several pictures when the accelerator was being installed. Some pictures about our sample preparation lab, the original setup of the instrument. Now you will see in next slides that we have a new line for nuclear physics. This is Arcadio, who operates and maintains the accelerator in front of the carousel. And here we have next month, for example, we will have a meeting with students that visit the laboratory. This is called Open Doors, and we receive many students to stimulate them to go into science. Well, the laboratory, the AMS system is based, well, here you can see the new line for nuclear physics. And this is our accelerator. Is the system, the AMS system is based in one MEV accelerator coupled to 2 mass spectrometers. No? And here you see the new parallel line with a new magnet to do nuclear physics. Here I am showing you the acceptance tests, and the levels of detection that we can go with, for example, for carbon-14, the decay constant, and the stable isotopes, the isobars, and the precision that we can obtain, and the lowest level that we can measure for carbon-14, for beryllium-10, for aluminum-26, iodine-129, and the isotopes of plutonium. The main research projects are carbon-14 applications, in particular for radiocarbon dating, as an isotopic tracer in environmental studies, and also for forensic science. We also are developing the applications with the beryllium-10 and aluminum-26. Later, Santiago Padilla will tell us about this project. And we are applying the beryllium-10 and aluminum-26 to aerosols, water, rocks, and sediments. Well, we are able to measure these isotopes, but these measurements are only under development. We haven't, well, we started with plutonium, but we have a colleague from us staying in Sevilla, learning to measure the plutonium. Iodine 129, we haven't done anything yet. We have the standards already. That's a start. And well, tomorrow we will hear several talks about the developments of projects dealing with nuclear physics and instrumentation in this new line that I am showing you here. As normally, well, the laboratories, the AMS laboratories show the percentage of time devoted to different applications. Here I am showing that archaeology continue to be the principal occupation of the machine. Well, I cannot see the figures, the colors, but we have a research line in archaeology, in nuclear physics, in atmospheric sciences, in forensic science, in environmental science, also different applications of carbon-14 in art, in earth sciences, and in environmental sciences with beryllium-10. Well, as you heard before with Tim, this technique started with William Levy, who proposed to measure the time elapsed since the death of an organism by measuring the activity of the carbon-14 in it. Here we have Levy in his lab. As Tim told us, Willard F. Levy won the Nobel Prize in 1960 for introducing the technique of radiocarbon dating. This technique has had a big impact in the social sciences, also in the physical sciences, but mainly in the humanities. And this technique is based in the fact that carbon-14 is a radioactive isotope of carbon found in all living organisms. Here I show you the decay line of the carbon-14, and the basis of the dating is that carbon-14 decays and the age can be determined by the remaining carbon-14. These are the basic formulas, and this T is the radiocarbon age. We can date organic samples as the ones that you have here: hair, leather, bones, feathers, horn, charcoal, natural rubber, soil, organic matter. But you can also date shells or corals, or also inorganic carbon dissolved in the water, and then do radiocarbon dating, water radiocarbon dating. So in order to measure the carbon-14 and carbon-12 ratio, and carbon-13 and carbon-12 ratio, carbon from samples need to be converted to graphite because it's the best way the carbon behaves in the accelerator. So here I show you, well, some pictures from our lab. Maria preparing samples, Sergio, Maria and I in the graphitizer. We need to clean the samples. We have to pre-treat them, physically cleaning, chemically. And then, well, normally the basic procedure is to treat them with acid, base, and acid. And then we take the clean carbon to this machine. It's an automated graphitization equipment. And, well, the iron needs to be conditioned. Then the sample needs to be combusted. And then the CO2 produced by the reaction is transferred to one of these reactors. And the graphitization, the conversion of the carbon to graphite is done in these reactors. And finally, the graphite is pressed in cathodes and taken to the AMS system. The analysis that we do here, we need to introduce the cathodes in this carousel. Each run in our lab takes 4 cathodes of the primary standard, the oxalic 2, which concentration is known. We also add 3 blanks with no carbon-14, prepared as any sample. We include 2 or 3 secondary standards of known ages, depending on the samples that we are going to. If these are Pleistocene samples, we introduce something of the same age, 12,000 or 15,000 years old. Or if it's, for example, pre-Columbian sample, then we introduce a standard of about 2,000 years. And in this way, we make sure that we are reproducing the values, the expected values of our secondary standards. And then for the calculation of this parameter, which is called fraction of carbon-14 fraction, carbon-14 fraction of the modern carbon, where modern corresponds to the carbon-14 in the atmosphere in 1950. We also use another parameter, which is called the percentage of modern carbon, which is this F14, carbon-14 multiplied by 10, by 100. Then we can determine our radiocarbon age using this formula. This is a result that we normally, there are many numbers, but I just want to explain you that this is one measurement that we call PASE, and is made out of 10 blocks of 5 seconds, or the accumulation of any counts. We have then the label, the kind of sample, the current, the carbon-12 current, the number of atoms of carbon-14, the ratios. We have a chi-square to compare the several errors, 2 kinds of errors, and the chi-square tell us about the quality of the measurement of each cathode. And finally, well, we can also determine the carbon-13 ratio in order to do some corrections that are needed to have the final radiocarbon age. In this other, I am showing you our final results. The 4 standards with its corresponding carbon-13, delta carbon-13, and the value of the percentage of modern carbon, the error, one of the errors chosen, choosing the highest error of the measurement. And finally, we convert the percentage of modern carbon to age, and also the error associated. And here we have the blanks. some secondary standards, and here I am showing some of the results of the unknown samples in this particular carousel. So carbon-14 also needs to be validated, and we have done several exercises to validate, but I am showing here one of these validations. We participated in an international intercomparison of carbon-14 standards organized in 2013 by the laboratory in Glasgow, Scotland, organized by Marian Scott. And I think we measured 12 samples, and all of them agreed with the consensus value, except for the one tree ring that was out of, not comparable. And well, if you could see this number, the correlation is acceptable, is very good. So we can say that our system is working properly. We recently also obtained, we were able to certify the laboratory. First of all, last week we obtained the certificate under the norm ISO 9001/2008, and later we had to update the certification, and we obtained the new certificate ISO 9001/2015, and also a quality certificate that is given by the university, our university. I'm going too fast, or? Well, now I will pass to some applications that we are carrying out in our lab. Many archaeologists have come to our lab with their projects, but I will just mention some of them. One is very interesting because we all are interested in knowing when the men enter in America. So how was immigration, and when, and the roads that they took. So when we have the opportunity to study this, for example, in the peninsula, Yucatan Peninsula, where are many sinkholes and submerged caves, and many deposits there. Is like an archive, historical archive, because there are many rests, many skeletons of animals that lived in the past, humans and also animal remains. Well, here this stone, I don't know if you can see the teeth here. This comes from the Valley of Mexico, here in Del Peñón de los Baños, which is a prehistoric site also that we are studying, but most of the samples are already petrified, so it's very difficult, no collagen, no enamel, it's very difficult to study. And the problem to study, for example, the tropical area of the peninsula of Yucatan is that it's very humid, very acid, the soil is very acid, and very humid and hot. So the bones, for example, are very badly preserved. But instead, in the submerged caves, we have found very good samples. Amazingly, they are very well preserved, some of them, not all, of course. But I will tell you a little bit about what we have found here. And also I will talk about one example of the studies that we are doing in pre-Columbian projects in Teotihuacan, which is a favorite of everybody because it's so impressive. I hope you will get the chance to go, Tim and Kita. Okay, then about the study that we have made in the submerged caves and sinkholes at Yucatan Peninsula, there is an increasing number of fossil bones that have been found in the last years, probably in the last 10 years. And the archaeologists here are interested to know how old they are and how the ecosystem were. So what kind of animals were. And well, one thing that I have to explain you is that the sea level has been changing, and there are caves that go very deep until maybe 65 meters. So we assume that every organism that we find behind these levels will correspond to ages older than the level, no? Than the increase of the sea level. So we have already, for example, only by the last increase of the sea level, any skeleton must be older than 8,000 years. So we have found, the archaeologists, the scuba divers, they have found pieces of charcoal, and many skeletons, hundreds of them. And for example, for one cave, the age of carbon, the age of these carbons here, that the archaeologists think they are like fires left by humans when it was dry. These caves, the organism or the remains that we have found or they have found are between almost 12,000 years and 9,000 years before present. So we can conclude that humans arrived to this region at the end of the Pleistocene. There are also some remains from animals, from Gomphotherios or this giant two-toed sloth, or this Genanthro, it's an armadillo, also horses, ecus, and all of them show ages older than 10,000 years. Well, this is younger, 8,600 years old. So all these animals are extinct already, but there are hundreds of them in the submerged caves of Yucatan. Well, as I told you, Teotihuacan is a favorite place because of its splendor, its magnificence. Here I show you the Ciudadela. And a few, well, maybe 10 years ago, in 2005, 12 years ago, the archaeologists discovered a tunnel underneath the temple of the feathered serpent, and they collect about 100,000 objects that have been dated and analyzed. They have a lot of job in the future to characterize all these objects. Very beautiful, some of them. And LEMA have analyzed around 50 samples of this tunnel, and I have presented before the results of this. For example, we have balls and animal jaws and charcoal and many shells. But now we have continued with this project. We were able to date the tunnel construction, the use of this tunnel. They closed and opened the tunnel several times, and then finally the last intrusion was around 430 to 530, and then after that, maybe a few years later, was the collapse of Teotihuacan. When the Spaniards arrived, the Spaniards arrived to Mexico, Teotihuacan was already abandoned. So we were able, with dating the charcoal and bones from the tunnel, we were able to put some dates to the tunnel. But at the same time, the Ciudadela there was like a first sanctuary, the Ciudadela, and this was completely demolished to build the Ciudadela that we know at present. And we wanted to know, well, the archaeologists wanted to know, sorry, if the new construction or the presence of these buildings, the old buildings, were contemporary to the tunnel, because everything was remodeled after to make a new Ciudadel very, very beautiful that we know now. Then we have charcoal samples from different stratigraphic layers in the old Ciudadela that we call pre-Ciudadela, pre-Citadel. And one particular finding was some bones from individuals offered in funeral rites corresponding to well, they correspond to this period between 150 and 380 of our after Christ. And this ritual, after the archaeologists, this seal of with these bones, the Teotihuacans seal the drains, making human sacrifices. And this, after the archaeologists, corresponds to the beginning of the Ciudadela construction as it is currently known. So we can conclude that, after these studies, that the pre-Ciudadela may have been built since the 1st century of our era and functioned for more than 100 years before being torn down to give place to the majestic complex of the Ciudadela as it is known today. Well, we also have people coming with their objects of art, and I would like to mention two of them. Well, the very first sample that we dated in LEMA, the first sample that we dated was an ibis, an Egyptian ibis. Believe it or not, we had an ibis in the lab, which was actually very old, with the mummy of the bird inside. So we dated the fabric used, and the bottom, a little piece of wood from the bottom of this leg, and it happened to be very, very old. Yeah, this is a calendar age before Christ. I put it in before Christ, 900 years before Christ. And another very beautiful piece of art that we dated also was from a mammoth incisive. It was sculpted with a fascinating scene of a princess. It's a scene palatial just over a century ago. The carving was done more or less a century ago, because the date is written in the bone, in the incisive. And we dated as the age was older than 4,000 years is from the place to scene. So this belongs to the museum, the Sumaya Museum, and they wanted to see how old was the incisive. Also, we have applied the carbon-14 peak bomb to analyze some piece of art. For example, this is a painting from Matthias, attributed to Matthias Geritz, who, after the death of his wife in 1958, he painted a series of paintings called Reflections in Gold. And one person came to the lab with several of these paintings to date, because they are printed in wood, so we could date the wood in the back of the painting. Some of the objects of art that we have dated are what is expected. Some of them are not. So this one it was easy, because after it was in the peak of the, or very close to the peak of the bomb, so it was easy to see if it was or not authentic, because it's very famous. It's very easy to make. I think any of us, if you have the golden layers, then you can make your own Matthias Geritz painting. Okay, so another application that we are interested in Mexico City because of the high pollution that we have is to apply the carbon-14 also to a new point of view to see the pollution using the apportionment of the carbon, if its origin is fossil or is contemporary. So even if the pollution in Mexico is very, very bad, no, the contribution of the human activities to the aerosols from the point of view of fossil versus contemporary is not well known. So we want to use the carbon-14 to determine the apportionment of fossil sources containing no carbon-14 and the contemporary or modern carbon-14. We are doing this in 3 rings and also in atmospheric aerosols. Well, I didn't put we have made some carbon-14 measurements in several trees from Mexico, where Mexico City is here. You can see the dilution of the carbon-14 for the presence of CO2 from the combustions of gasolines and diesel and etc. And also we can this is a picture of the 3 rings. And also we have collected aerosol filters in different places of the city. This is the area of Mexico. And we have collected aerosols in different places in the city and also in Cuernavaca. And this, for example, here I show you the fraction of carbon-14, and you can see, for example, Cuernavaca is very biogenic, very biological, very green. We have the contemporary, the fingerprint, and this is Mexico City. And also you can see that every place in Mexico City can constitute a microenvironment, because the city is so huge that we have local environment in the city. So for example, Iztapalapa, we can see that we still have a lot of cooking with wood, and we can see the signature there. And Mexico City, the center of the downtown of the city and university, here in UNAM, that we have a signature more toward the fossil side, no? Many CO2 that comes from the combustion of gasoline and diesel and other activities, human activities. So Elba, my colleague Elba Ortiz, will talk more about this project, more in detail of what we are doing now. And finally, the last application that I want to talk about is a new application that we are working on. It's about the hydrological applications with carbon-14. So the radiocarbon dating of dissolving organic carbon in groundwater in order to date the age of the waters. We have a big problem, I hope you can see this complicated figure, but you can see here in one corner that 80% of the water that we consume in Mexico City comes from wells. So, and 20% only from superficial waters, no, from the Cutzamala system. So we have been over-exploding our aquifers. So we have several kinds of aquifers in the valley. We have very, very shallow aquifers. We have aquifers that were called before profound, deep, but now we have a deeper aquifer of 2 kilometers deep. Then the hydrology want to characterize, and now that we have this laboratory of AMS, pues it's a great opportunity to start characterizing our aquifers. We have about 665 aquifers, no, or 400, I don't remember the number, in all the Valley of Mexico, which is not only the Mexico City, but also several states surrounding but of course, the city that take the most of the water is Mexico City. So water comes from wells very far away, and we are having a big problem of sinking the city. Some places are 7 meters below the original level, and now the bottom of the lakes, for example, are above the bottom of the surface of the city of Mexico. So this makes very problematic, no, the disposal of the waters and many other problems. How do you say the water? Yeah. Okay. Well, I am done. I only want to make some conclusions. Most of our projects are interdisciplinary. Also, we are developing basic research. And in my opinion, AMS in Mexico is starting to develop and offers great opportunities for interdisciplinary applications. And well, thank you for your attention.
Questions? Thank you, Corina, because you let us know very interesting application about AMS analysis. So I didn't get it exactly if you mentioned that you couldn't find enamel in the skull that was petrified. You couldn't find enamel, or?
Well, no, we were looking for collagen. Yeah, we have been looking for collagen in some of these. Most of the time they bring us bones. Actually, these teeth that I showed you, we haven't analyzed them yet. Hopefully, we can find some enamel or collagen, but they are all petrified when you treat them with the acid. They disappear completely.
Any other question?
So in the caves that are flooded by the sea, did you find any human bones or just
Yes.
animals?
Human bones too. There are like 10 skeleton, 10 to 12 skeleton that have been studied. Mhm.
And they were?
From about 9,000 to 12,000 years.
Okay,
Mhm.
that's good. Thank you.
More questions?
Two curiosities, Corina. The first, a red number in your table. You show a table, which means the red number in the first table of that you showed.
Yeah, the chi-square is out of the limit. When the chi-square is too low or too big, or higher than 1, you expect your chi-square to be close to 1. So when you have two errors that differs too much, then you have to look carefully to that number. So
Okay.
that's why it's in red. We
Okay.
put it in red. Uh-huh.
Y-
So, but
another-
of course, I show you the best results that I have.
The other questions is just a curiosity that was asked me for by Javier, that you speak about the origin of man in America. Why to investigate there, considering it comes from the north, or there are some other theories, or?
When you study where you find the material, no?
we have colleagues, archaeologists that are studying the pre-ceramic men in America. Well, Cyprian doesn't like this this name, but from the north. But it was also a question if the first men in America arrived to the peninsula of Yucatan.
Yeah.
No, because we are in Mexico. So, and also the archives that we have there are perfect material to study because they are very well preserved. You can study what kind of animal. You see the preservation state is so perfect sometimes. I mean, for at least in the form, no, that the water was increasing so slowly that the organisms remain there in the position that were as they were dead, you know, perfectly, and even you can have the stalagmites growing on the bones, no, showing that the caves were dry when they were there. They died. So it's because the great amount of material that is found that we can study what happened in the past, but you don't find this everywhere. No, it's very difficult to find. I don't know how the archaeologist Cyprian can tell us how he found his cave, no, his Pleistocene cave. I don't know. They know how to do.
Well, thank you, Corina. And now we continue with our next talk, the role of AMS dates as strategic weapons in the paradigmatic clashes and on academic battlefields. The presentation of a Wiki user by Cyprian Ardelean from the University of Zacatecas.
¿Dónde? ¿Me lo ha hecho una bolsa? ¿Se escucha? Okay. I will not text during my talk. I just need a clock. So, thank you very much for inviting me again. This is my 5th participation in the workshop. So at least you have a regular client, like the pubs, you know. I will start with a very important connection with Dr. Jules' talk. Do you guys like SpongeBob SquarePants? Bob Esponja, la caricatura. Do you know that the reason why they are in the Bikini Bottom is because the Bikini Atoll was a place for French nuclear tests in the Pacific. So they are all mutants. And that's the reason why every episode starts with a guy speaking with French accent. You know, and now everybody in the world in YouTube knows about it. So I came here to throw a bit of temper tantrum, as I always do. I promise I will not throw microphones away at people. I am an archaeologist. Do we have more archaeologists here? Or archaeology students? Anywhere? Only 1, 2. So yeah, so I can say whatever I want. Okay. So when you go around the world, you will see very fancy archaeologists who do very fancy lab work and who are able to collaborate with scientists. People doing isotopes, people doing geochemistry, people doing geophysics, etc., etc. Well, I don't do any of that. I'm a specialist in lithics. But if I was to define myself, I consider myself a field archaeologist. The good part of being a field archaeologist is that I have a very adventurous life. So I can look posh in meetings showing interesting photos. The bad part of being a field archaeologist is that I depend on you, the scientists. So, and it costs me money to do things that I was not taught to do in school, you know. And this is why I always come to this workshop to talk about a tale of two different worlds that actually involves a separation between archaeology and science from school. And that creates both a symbiosis and a crisis between the two. Now, the problem in Mexico, and I'm referring only to Mexico because I'm not really, I have no reasons to start talking about other places. The national paradigm here is that archaeology is anthropology. Well, this is something that was said in the United States. The thing is that in Mexico it was somehow misunderstood because anthropology is what social anthropologists do. If you ask 99% of anthropology students, they will give you a description of anthropology as social anthropology. So, in that case, archaeology is more or less why social anthropology is doing. The problem is that the administrators are understanding the things exactly this way. So, archaeology is just another blurry thing in humanity. Sorry, I'm thinking that the Canon is too close to the screen. That's why you don't need money for analysis. That's why you don't need labs, because you are in the same academic area as the poets, the philosophers, the historians, and you can write poems under the tree. You don't need science to do that. So it's been a catastrophe for archaeology to be considered humanities. So archaeology is a science and should be taught as a science, not as a humanities. Or we should reconsider the idea of humanities, because definitely archaeologists are not taught science. So we are finishing our undergraduate studies and we are handicapped and totally at the mercy of scientists. And that causes demotivation, and that causes conflicts, and that causes a lack of jobs for the archaeology students. So, whatever. There are several problems that lay at the bottom of this problem. It's like the bikini bottom. The orality cult in Mexican academia. We have so many congresses, symposia, colloquia, that actually if you look at the academic calendars, you will have 5 or 6 different events every single day overlapping somewhere in the country. And that happens in detriment of writing. So the good thing of that is that in Mexico, the congresses are fabulous. If you go to Japan or if you go to France, they are absolute idiots in organizing congresses. So, but if you come to Mexico, if you go to Oaxaca, that Itzel is here, you can be treated as kings. The Congress will have lots of food, and everybody knows how to organize it, because by the time you finished kindergarten, you have already organized 5. You know, but you never write a paper. The students are not able to write a peer review focused paper, but they're able to speak. The lack of scientific journals in Mexican archaeology. Do you know that in Mexico there is no scientific journal for archaeology? Not a single one. So that's a terrible shame for the country who has the highest number of archaeological sites in the world. You know, we have 500,000 archaeological sites, of which 191 are opened to public only. But there is no scientific high-impact journal. So that causes 2 problems. There is no obligation for archaeologists to be able to write scientific quality papers, and there is no behavior around the obligation to write high-quality paper. And 2, there is an institutionalized procrastination. So it is considered valid to consider a paper presented orally in a congress as a production, and that doesn't happen elsewhere in the world. right? Your production is what you write, and in Mexico, your production is what you speak in archaeology. And you are never able to access other people's production if you are not present at the moment when it was said orally, which is stupid in the 21st century, right? We will see how that impacts the relationship between archaeologists and labs like LEMA. Now, so the effects of these conditions are that are codependent and blind users of science. So basically, it's like going to a pharmacy, to a drugstore, right? I give you the sample, you give me the result, and that's magic. We finished our relationship. So I go home, I will print my date on the t-shirt because probably it's the only date I will ever do, right? And I consider myself, I contributed to science. Absolute dates are not something normal among archaeologists. This is something that you must understand, that we don't do radiocarbon dating. Everybody in the world, your aunt, your uncle, will see in Discovery Channel that archaeologists do dating. We don't in Mexico. Actually, those who were here in previous workshops could see how happy a couple of archaeologists were because they finally had their first radiocarbon date after 60 years of investigation in their site. Last week, the visitable archaeological zone number 191 was opened in Zacatecas. It costed millions and millions of pesos, and they have zero radiocarbon dating. So some institutions like INA, they lack the financial chapter for such analysis. So they cannot pay for radiocarbon dating because they cannot justify it. They have specific partidas financieras for fuel, for renting trucks, for paying people, for buying cement and whatever, but it is not possible for them to pay for radiocarbon dating because they don't have that in their financial schemes. So it's impossible, right? The radiocarbon dating is not understood. So the archaeologists don't understand how this thing works because they never had a class at school about how it works. And those who do, because they learn it by themselves, not because the universities taught them. The dates are treated as magic products. The archaeologists, we believe that once we have one date, we have solved all the controversies. You should speculate on that. You should become like sort of a priest in the views of archaeologists because you are like witches. So, and also the worst of all is that there is no pressure from the peers to have a serious use of radiocarbon dates, like it happens in, for example, in Paleo-American archaeology in the United States, or like it happens in Neanderthal-related now artwork and stuff in Europe, where there is a continuous pressure to use the dates properly that does not exist in Mexico. You will never, ever, ever see a debate between Mexican archaeologists around radiocarbon dates. So the problem is that ideally archaeologists must understand how radiocarbon works, and also the C14 labs must understand archaeologists, right? So there should be somebody in the labs dedicated only to the liaison with archaeologists, because physicists are not necessarily required to know things about archaeology, but archaeologists definitely don't know about radiocarbon. We are doing like jobs like they are blind from both sides. And this one should not exist. Of course, I'm talking about beta here, right? The strictly commercial relationship between academic labs and academic sciences should not exist. The commercial labs practice this all the time, right? But the academic labs should avoid this kind of treatment. They should keep a sort of dialogue with archaeologists. Let's see, what do we have here? How has been the sample extracted? Can I see the stratigraphy? Can I look at the context? is this charcoal good for dating, or should I choose the bone? Is this shell suitable for dating, or my result is going to compromise my prestige? Right? How often do we think in these terms? Well, the thing is that out there, the peer reviews will judge you under these terms. So the mistakes we normally commit in archaeological work, and that the C14 lab should talk us away from them, is mistake number one. There is an excessive cult to personalities in academia, especially in Mexico. It was very common in the Soviet Union. It's been very common in Eastern Europe, where I'm from. And normally, like for example, in Mexican prehistory, there's a mantra here saying, Lorenzo said it all. Right? Jose Luis Lorenzo, the patriarch of Mexican prehistory, who's been completely refuted many years ago, but it's still considered like the landmark. Now, the problem with that is just consider that that was in the 60s. And that was just like the next day after the radiocarbon was invented. How can you rely on dates that are 50 years old, right? Well, the entire discourse today of the Mexican prehistory is based on dates that are 50 years old. Mistake two, sticking to relative chronologies. Archaeologists are obsessed with seriations, and if you go to 99% of the visitable touristic archaeological zones in Mexico, the entire chronology of the site is based on suspected chronologies based on artifacts, not on absolute dating. So we don't have the culture to go for dating. Why? Because it's considered that the people before, I mean our professors, the people who are sort of mummies today, they have the right to be considered as the landmark until they die, or sort of that. So you don't go to do dates to offend your professor, because what if you refute his theories? That's the real behavior in academia, which is dangerous. It should not be allowed. Mistake three, we think a radiocarbon date is forever. Well, it's not. The dates must be redone every certain number of years. You need to redate stuff, and you need to draw away the dates that have very, very large uncertainties. Now, what do you say about something that would look like that? What can you say about a date done in 1977 saying that a site is 25,000 years old plus minus 3,000? Well, that's the kind of date we have at Tlapacoya. That's the kind of dates we have at El Cedral. That's the kind of dates we have at Valsequillo, plus minus 3,000. Right? Who in the world will ever accept that today? Because it's absolutely outrageous, right? To have that kind of dates. Well, Needlecroft Rock Shelter in Pennsylvania, who's been the first site in North America to treat in the Clovis first paradigm, has that kind of problem. Their dates have very, very large deviations, and that's one of the reasons that they are still struggling 45 years later with the acceptance of their site. Mistake four, we think one date is enough. It's not. When you need lots of dates in order to be considered for a discussion. One date makes nothing. So if you have archaeologists who come with one sample and never show up again, you should have the right to ask them what happens with that site. Are they dating with somebody else, which is what the way it should be? Are they trying to corroborate your dating with other labs' dating, or why is that they are okay with one date? The problem is that if you get involved into a project as a lab, it should be, it's advisable to become actively involved in how the scientist, the archaeologist, is going to use your results. And something that archaeologists don't understand is it's like when you're going on the street today and you are assaulted by a criminal who has a machine gun with him. What would you do? Hand in the wallet or take your knife? That would only piss him off, right? So you better just be cooperative. Well, that's what happens with the dates. If you have one date, you will not solve the problems. You will just attract the attention of the people who are the radiocarbon sharks, right? And they will try to destroy you based on the dates, because that's how your paper will be evaluated, if you ever write a paper or you will just say it in congresses, right? Mistake 5, we think one lab is enough. Well, having one lab, it's extremely badly seen today. It's considered data manipulation, especially among the peers who are specialized in peer reviewing papers in early prehistory. If you don't date your material with different labs, they consider that you have your friends in that specific only lab that you use, and you are manipulating the results. So this is a normal accusation you will receive, especially when the lab is next door from you, like in certain other institutes in this university, and you don't want to corroborate the results from that lab with LEMA results, for example, or with Oxford results, or with Arizona results, because those are your friends. So how credible is your date if all your dates come from only one lab, and that lab is located 50 meters away? So that's not credible. For me, it's not credible. When I see that in the papers that I have to review, that's a no immediately. They must redo the dates with other labs. And that's actually one of the problems with one of the skeletons in the Mayan cenotes. There are two rival projects there who hate each other. So one of the projects dates their material with somebody, and the other project dates the material on themselves, because the guy who discovered the cave owns his own lab. So all his dates are his. Now imagine the credibility there. So it's not okay. So, well, this is what really annoys me, and that should annoy you, because I've seen LEMA dates manipulated like this. They don't put the raw radiocarbon, only the calibrations. Now, everybody knows that that's insulting and unacceptable, right? Mexicans know what that means. So you cannot do that. It's illegal. You haven't received a result signed by the lab. You must provide the raw results exactly as you received them. No, the archaeologists don't do that. They take only the calibrations because they are wide enough to play with them according to their own arguments. Do you see how prehistoric we are in our thinking? Now, you as a lab should have the initiative here and say, excuse me, but we will not date another sample for you if you don't treat our results correctly. So just a few weeks ago, I received the third revision for a paper written by people from UNAM. Okay? And I rejected it because it was the third time that I asked for them to provide a table with the raw results of the data and refused. I am sorry, but that cannot be, right? The AMS data should be used extensively and dynamically, not only after termination investigation, but as a guiding tool during the research. So you are on the field, you found something, you don't know how old it is, you don't know if it makes any sense to continue your work, date it first. And this is a special dedication to the people who do mammutology in Mexico. You know, Mexico is a place where people love to dig up mammoths. Doesn't matter if they are associated or not with humans. As soon as it's a mammoth, it must be rescued. It's like we are trying to revive all the mammoths that are buried under there, right? So it's like a national census of mammoths. So there are horses, there are ground sloths, there are a lot of things that nobody cares about, but if it's a mammoth, millions of pesos go into the excavation of a mammoth. Why? Did you date the bloody mammoth first? Do you know if it's in the range of human occupation, of possible human occupation? What if the mammoth is 1 million years old? Why would you dig up a mammoth if we already know how the mammoths look like, what they ate? We know almost everything. So the output of data that you can extract from a mammoth is very low compared with the amount of money that costs to dig up a 50-ton animal, right? So that's something that also the lab should step forward. And when you hear that a mammoth has been investigated and INA goes there with 10 trucks of people to excavate the mammoth, you should say, let me date the thing first. Maybe we are lucky enough to find collagen in it, right? That never happens, actually. Anyway, but anyway. Well, the prestige and reputation of the lab is something that has a lot to do today. Not all the labs have good fame, and the labs must be opened to this thing. Don't cover your ears and try to avoid this issue. Many papers are rejected because the labs used have bad reputation. So a lab must consider how is our reputation today among this branch of users. Archaeologists, environmentalists, hydrologists, etc. Right? So going fast to an example, a concrete example from my area. I'm working in this godforsaken area from northern Zacatecas. It's at the border with Coahuila, and right there we have a massive cave. Nobody has ever heard of it because it's still a secret, right? We are still working on it, and I cannot tell you all the details. So you will never tell, right? I mean, LEMA is an active part of this research together with other labs, and it's a 17 institutions research from 5 countries. It's a very big thing that we are cooking there, and it's coming out soon, so soon on theaters. So it's an area that I've been investigating for 10 years, and finally after 10 years of wasting money, I realized that the place that I was actually looking for from the very beginning, it was the first I had found. So I had found the place first, answering some question there, how archaeologists do the work. I found the cave first, and then I found 36 more sites that were all recent in time, and the cave was the old one. So I should have stopped there from the very beginning. But the thing is that I dated most of these sites in order to know that they are not old. So I'm not assuming they are young. I dated them. So that's why I concentrated on this cave, which is named Cueva del Chiquihuite. It's situated on, I mean, this is the digital elevation model. It was a lake here, a Pleistocene lake, and then you have the mountains. And the cave is the highest archaeological site in North America. It stands at almost 3,000 meters of altitude, and nobody would have ever imagined that there was anything up there, right? But I mean, the difference between this point and this point is 1,000 meters. So, and here we are about 25 kilometers of distance from this point. Right? The cave is not where the arrow indicates, because I'm trying to mislead you in case you want to find it. Right? But it's at this level. Right? You see how secret I am? That's because I also work for the Brits, so I'm like a double agent. So this is the vision of the cave from inside. This cave, the surface of the cave in the other gallery has two chambers. LEMA dated both of them together with other labs. But the Pleistocene occupation that we have is in the main gallery, this one, that receives lights only for 2 hours a day here now. This is the very moment when the light comes in at 4 p.m. The other chamber has small stalagmites growing on top of this debris, and we dated with uranium series, the smallest of the speleothems. It's 700,000 years old. That's speleothem. So that cave is millions of years old. It's a very, very weird cave. It formed by the constant peeling off of the roof. So the cave moved up from probably 1,000 meters below. Do you know what I mean? So every new stone coming off the roof contributed to the rising of the floor. So the cave moved up. So it's not a typical dissolution cave. It's a collapse cave that's probably like 4 million years old. And the stratigraphy there is extremely difficult because it's gravels. It's gravels over gravels over gravels over sands over gravels. The OSL signal in the sediments is very, very weak because of the lack of light. It worked amazingly well, even if it's so weak. And we have tons of artifacts there from top to bottom, but I cannot tell you the age. You'll have to wait for the paper we are about to publish in Nature, and it will challenge everything you know about the peopling of America. So we have passed the revision process, and now we are dealing with the revisions. And these dates that you see there, 10 of them belong to LEMA. You see that the Bayesian model is very, very nice. Everything fits with everything. There are some curious stuff in the lower components, but I mean, it's normal because you have a redeposited section in the lower part. However, I cannot show you the calibration here. I need to remain secret for a while. Nevertheless, these 52 dates are from one single trench in one site for the first publication. I mean, this is already more than most dates you have in all the other archaeological sites in Mexico. Exaggerating, of course. But normally people come out with one date, they cause the stir, they cause the discussion, they cause the controversy, and then they spend the rest of their lives trying to deal with the controversy because they become famous. Right? So we went the other way. We were very careful in how we selected the samples. We involved several laboratories. We are proving that blind dating from different laboratories, they don't know about each other, gave the same results that match just amazingly well with one another. But this is a paragraph from the review. So let's analyze it, like in English 101. The authors appear to have used 5 different radiocarbon dating laboratories: Oxford, Beta, LEMA, ICA, and Paleo Research Institute in Colorado. We know labs don't do the same thing, and that some labs certainly produce far more reliable age estimates than others, right? Not saying it, the reviewer says it, and this is the nastiest one. Satisfying the reader that robust and comparable ages are being produced by different laboratories, right? We are satisfying the reader because otherwise they will be pissed, see? Are especially important because the lowest, and now comes the hit, the lowest 3 radiocarbon samples are measured by 3 different labs, none of whom are highly regarded in the scientific community. So this is the kind of stuff you receive back from the reviewers. I mean, the people at PRI, the people at ICA, the people at Beta will say, WTF, right? I mean, what do you mean with that? Well, I'm the picky user. That's what the title of my talk says. I need to adapt to this because otherwise my paper gets rejected, right? So why do they specifically doubt of these dates is based on the prestige of the lab, right? So if I didn't use 5 different laboratories, I would have been killed immediately, because it happened before and we know how it works. So they will ask you to do different. So if you want to collaborate as a lab with scientists in a very debated topic, I mean, things that really cause controversy, not things that are self-evident, things that cause controversy, and you want to co-author it as a lab, you must demand the user to send replications of the samples or other samples to other labs. You need to go above and beyond your pride as a lab and try to involve other labs, even if it's commercially, only because the peer reviewer will ask you for this kind of standards. So thank you very much. I hope this was useful.
Thank you. Thank you very much, Cyprian. Do you have questions or comments?
Oh, well, thank you very much, Cyprian. This is a very provocative talk, as usual. There are a few Mexican journals that have impact.
Not archaeological ones.
I mean, in the whole scientific.
Oh, yes.
There are only a few. In physics, there's 2. One is the Revista Mexicana de Física, which has a very high impact factor of 0.1, and the astronomical, the astrophysics and astronomy, which has a relatively very high impact factor. It's very hard to have a journal, but we can try. There are other journals at the university that are trying hard to do it, and if there's no one, it could be interesting to give it a try at the university. We can talk about it later. But then several 100,000 sites, archaeological sites in Mexico, so it will be interesting to be able to date a couple of samples from each site here at LEMA. Then we would need to have funding from federal agencies anymore. The thing is that we need to make some sort of a challenge, as you say, to the archaeologists to use seriously carbon dates. And if you think there is a way we can do it, we're happy to help.
I don't doubt that. And my mention about the lack of scientific journals refers only to archaeology. I mean, there is none, with or without high impact. I mean, Arqueología Mexicana is Sanborn's magazine. I mean, that's not science. And several others are just local with no distribution. They're not really, I mean, geologists, geophysicists, they all have high impact journals. But the fact that archaeology lacks one demonstrates the predominant optic in Mexican archaeology, which is oral and not written.
Any other question?
I was thinking about commenting on the quality of the labs, but I won't. I wanted to emphasize your comment that people should report the raw data and the raw radiocarbon dates, not, you know, I mean, I'm the editor of Radiocarbon, so we really hate people just reporting calibrated ages because, as you've already seen, the calibration changes with time anyway, not to mention...
Or putting the calibration without saying with which curve.
Yes, exactly.
Right.
So you have to state the raw data and how you got to the calibrated age. And then somebody else can go back and reconsider it later if they want to. And the other thing you mentioned about always following up with the dates later, I think that's also very important because that's also something I would emphasize. So it's really just a comment.
And there is something that I forgot to say. There are some strange challenges also to us. I sent 2 of those samples you saw in the Bayesian were heading for your lab. And they were stopped at the border because they were bones. And DHL and UPS and the Mexican mail are forbidden to transport bones since they discovered human remains being exported to the US from kidnapping. So my bones twice were returned from the border because they said that I cannot prove, even if I had all the INA paperwork, that I cannot prove that my bones were archaeological. And they said, I mean, it says they're archaeological there, yes, but what if they are human ones? Well, what if they are? I mean, but they are archaeological, right? So I had to physically take them to another lab where I had already a travel to Europe, so I took them with me. There was no problem with it, but I could not mail them. So there are stupid challenges as well. Those were charcoals. Yeah.
Another comment, Laura?
Thank you. I agree with most of the things you said about the separation between archaeology and science in Mexico. But I also would like to mention that there's been an effort from both sides, at least from some archaeologists, I mean like you and other examples, to try to close this gap between these two kind of disciplines. And especially in the last, I would say, 8-10 years, we are trying to write some radiocarbon methodology, all the radiocarbon basics in Spanish in order to invite the archaeology community to start using radiocarbon dates with this, with the rigorous that it should be, like all this reporting the lab code, reporting the conventional age, reporting the fractionation data and everything. I think we are like walking towards the right direction.
Slowly. Yes, we are.
More questions? Well, thank you very much. And our next talk is beryllium 10, a new research line at LEMA, and it will be given by Santiago Padilla from UNAM, from our laboratory in the Institute of Physics.
¿Cuál es el puntero? Este no. Vale. Avance. Okay, thank you. I'm Santiago Padilla. I'm going to talk about the preliminary results of beryllium 10 in a new research line at LEMA along the So, as a brief introduction, it's fine. Yes. In a brief introduction, when the cosmic ray particles enter in Earth, the interaction with the atoms of the atmosphere and produce a secondary particles cascade. Those secondary particles produce radionuclides by spallation reaction in atmosphere and Earth surface. In this case, beryllium 10, meteoric or in situ, by this nuclear reaction. The production of the radionuclides is affected by the solar activity, the solar and Earth magnetic field, the latitude and altitude. It's for this reason that the production is higher in poles and lower in equator. In this table we can see this table shows the typical levels of the concentration of beryllium 10 in Earth for several matrices, such as quartz, sediments, aerosol filters, rainwater, or ice core. The levels of concentrations depends on the production way, if it's atmospheric or on the surface of the Earth. So, why is important the study of beryllium 10? Beryllium 10 is a high half-life radionuclide. La camiseta. Okay. Okay, so beryllium 10 is a sorry. Beryllium 10 is a high half-life nucleide and is found in nature at trace levels. It's a powerful tool because it's a very important trace set on Earth and is common used as geoclinometer. Beryllium 10 finds application in several sciences such as geology, geochronology, oceanography, meteorology, or volcanology, among others. The feature of these radionuclides make that the conventional mass spectrometry is not able to measure them because this kind of or system are not able to separate the isotope and isobar. In our case, it's boron 10. For this reason, the AMS is the technique adopted to measure this kind of radionuclides because provides us a high sensitivity and a good selectivity because AMS is able to separate the isobar and the molecular interference almost totally. The magnetic and electric elements of AMS are able to query and select the ions by mass and energy. And finally, the information that AMS provides us is the isotopic ratios. In this case, is beryllium-10, beryllium-9. So this is the accelerator of LEMA. It's a tandetron accelerator of 1 megavolt. The AMS is divided in 3 zones. The low energy zone, where is found the cesium sputtering source, where the ions are produced. The first electrostatic analyzer, where the ions are selected by the energy and charge. The first magnetic filter, where the ions are selected by the relationship of energy, mass, and charge. The accelerator is where the stripping process is produced. In this process, the beam in the incoming beam interaction with the stripper, in this case is argon gas, and change them in charge, and after are accelerated by the potential of the accelerator. In the high energy zone is found the second magnetic filter, the electrostatic analyzer, and finally the double anode ionization gas detector. Beryllium is introduced in AMS as beryllium oxide and is extracted from the ion source as beryllium oxide minus. In the ion source also formed the interference, the isobars is boron 10 as boron 10 oxide minus also. So both isotopes can be separated with the use of a passive absorber in the beam line. The passive absorber is a window of silicon nitrogen with a thickness of, in this case, is 75 nanometers. The charge distribution in low energy AMS after the stripping process and passive absorbers is, for example, 1 plus and 1 plus, with a transmission of the beam after the accelerator, after the stripping process of 56%, and with a transmission of the ratio in beryllium-10, beryllium-9 of 6% after of the passive absorber. Also, the charges are produced as 1 plus 2 plus with this transmission, 2 plus 1 plus, 2 plus 2 plus with this transmission. The measurement of beryllium-10 by AMS is carried out taking the beryllium-10 till the detector and the beryllium-9 till the Faraday cap is located after the second magnet. To can measure both ions, the system comes with a bouncer injector in this point, in this magnet, what introduces a potential stopping the beryllium-10. So the beryllium-10 takes the same energy that beryllium-9 and is able to pass through the magnet in the same conditions that beryllium-9. So the switching of this potential is in short times. So this way, both isotopes can be measured in quasi-simultaneous way. Sorry, here in this point is the passive absorber. In the passive absorber, when the beam reaches the window, both isotopes lose energy depending of the zeta. In this case, as the zeta of boron-10 is higher than the zeta of beryllium-10, the boron-10 loses more energy than beryllium-10. This way, we can separate both isotopes. The optimization of the all of parameters of the system, the parameters of magnets, ISAs, and lengths, was carried out within with several standards, with those with these different isotope ratios. These standards were provided by Nishizumi from University of California, Berkeley. In this graphic, we are represented the nominal ratio of the standard, the original ratio of the standard, against the ratio that was measured at LEMA. We can see the R square is 1. We can say that the optimization of all of parameters of the system is right. So they are the typical spectrum of beryllium-10 in AMS. Are represented E is the energy which the particle reaches the second anode, and delta E is the energy which the particle reaches the first anode. So we can see clearly two peaks. The boron peak is totally clearly separate from the other peak is the beryllium particles. So they are separated by the use of the windows of the passive absorber. This spectrum is for standard. This is for a blank. We can see that the blank doesn't have beryllium-10 or a little bit beryllium-10. And this is, in this case, from a natural sample of aerosol filter. An important step for the measurement of beryllium-10 is the radiochemical procedure. This is a general diagram. When we take the sample, this one has to, we have to add beryllium-9 carrion, because beryllium-9 is so scary in nature, and we need to have an equilibrium between beryllium-10 and beryllium-9 in the sample to be measured after in the AMS. So the difference of the radiochemical procedure depends on the origin of the radionuclide. When the meteoric beryllium-10 is produced, it's done inward to the surface, and it's deposited in the surface. So in this case, the leaching is a single leaching with HCl to extract the beryllium, sorry. However, in situ production, the beryllium-10 is forming inside the crystal structure and is retained in this site. So that for this kind of sample, we have to make a digestion with HF to break the structure of the rocks, and after to extract the beryllium. As well as every sample has its own pretreatment of the sample, but this is the basically difference. After of those parts is the same for all samples. The sample has passed through 3 resins: anionic resin to remove iron, cationic resin to separate beryllium and aluminum, and cationic resin to remove titanium and purify the beryllium. After a precipitation with ammonia and iron to obtain beryllium hydroxide, calcination to obtain beryllium oxide that we see we have seen that is the way to introduce the beryllium in the AMS. The sample is mixed with niobium to get enough conductivity in the ion source to produce the ions. And finally, the measurement by AMS. And the preliminary result of beryllium-10 first aerosol filters. The aims of this sample are the determination of beryllium-10 at LEMA, the concentration of meteoric beryllium-10 in Mexico, and provide new data about beryllium-10 in aerosol filters. The sample were quartz aerosol filters with a mesh size of PM10. They were taken during 48 hours in approximate volume 6,000 meter cubic of air per filter. They were carried and they were taken in November and December of 2012, because it's the cold dry season. Three sampling sites were chosen here in LEMA, Toluca and Cuernavaca with this altitude and this latitude. And this is the radiochemical procedure that was carried out. This radiochemical procedure was taken from the literature by Auer, and two new steps were introducing a calcination because our sample has too much organic material, and a digestion with HF to dissolve the quartz of the sample. After the same resin, calcination, and finally the measurement by AMS. This is the Fourier spectrum obtained with these samples. And in this spectrum, we cannot make the difference between the beryllium-10 particles and other particles, and with a lot of particles reach the detector. So this is a very dirty spectrum, and we cannot take out any information for this spectrum. After, our chemical procedure was adapted and more adjusted in our laboratory, and today we are obtaining this spectrum where we can distinguish clearly the beryllium-10 particles from the other particles. So this is a good spectrum. Okay, in these graphics, I represented the data of the sample when the sample were taken, and the concentration of the sample in atom per meter cubic. We can see that for Toluca and LEMA sample, the behavior of the sample are so similar. This is not the same in Cuernavaca sample, but the importance of these results is that for all the samples, the concentrations are so similar. So in 3 points, in different points in Mexico, the results are so similar. This table shows other studies of the beryllium-10 in aerosol filters in other latitude and in other altitude. For example, in Alps, in Germany, in Japan, or in Spain, comparing with our results. The important information of this table is that all the samples are in the same order of magnitude in concentration. So that means that the data obtained at LEMA totally agree with those obtained by other studies. So that means also that our chemical procedure and our optimization of the parameters of the system are right. Now, other samples, in this case it's volcanic rocks. After the production of the radionuclides in atmospheres, the beryllium-10 is downing ward to the surface and finally is deposited on the bottom of the sea. After, it's transported by the tectonical plate and is gone out from the volcan by the eruption. With this sample, the aims are the determination of beryllium-10 at LEMA, the concentration of beryllium-10 in this kind of sample, and assess the time that the beryllium-10 spends during the process. For this experience, 4 samples were taken, Cebuco and Seattle from Mexico, and sample volcan samples, San Salvador and San Miguel from El Salvador. The first test is the only test we have done. The first test was carried out with Seattle volcan. For this test, 5 molecules were shifted to a different grain size. In this case, 300 micrometers, or size between 120 to 120 micrometers. This is our radiochemical process. You can see that is so different that for aerosol filters. First, the sample is crushed to this grain size. After, 10 grains for every aliquot were taken. Afterward, we have to clean the sample and leaching with HCl, because we have to remove all meteoric beryllium that is depositing in our samples, because our interest is take out the beryllium-10 is inside of the rock that was transported for the volcan. Okay, so this meteoric beryllium can contaminate our results, so we have to remove it. After cleaning again the carrier, the digestion with AF, because we have to break the structure of the rocks. This kind of sample, the volcanic samples, have a lot too much iron, so we have to remove it. In this case, to remove it, we precipitate the iron and beryllium together, and after, with sodium hydroxide, we want to redissolve this beryllium, but not the iron. Okay, and always raising calcination and measurement. After the radiochemical procedure, the sample were measurement by AMS, but no current was obtained, so the beryllium was lost in some step of the radiochemical procedure. In this case, those steps or this step is, we think, is the problem. And if we see this pH diagram, the beryllium hydroxide is precipitated at this level of pH between 6 and 13, but in this little space of value of pH, the beryllium is redissolved. So, with this step, we want to redissolve the beryllium. The problem is that when the iron is precipitated, forms a structure, and the beryllium is inside, is retained inside of that structure, and we have to take off the beryllium, redissolving the beryllium, reaching this this pH value. It's difficult, and in this case, this step didn't work. But they are good news because we got spectres, and those these spectra are, how we can see so clearly, all of the spectra. We can see the bottom 10 peak, and we cannot see, but I say you, in some rows are beryllium 10. So they are good news. We have to repair the radiochemical procedure to take out the more possible beryllium, and we can see that we can got a good spectre. So this is in our next test. For nuclear physics, the production of beryllium-10 from beryllium-9 for this nuclear reaction was carried out. The aim of this experiment is the measurement of the neutron thermal capture cross-section on beryllium-9. For this experience, 4 samples of 8 milligrams each one of the beryllium standard dissolution for ICP were taken, and this is the experimental procedure, precipitation, calcination. The samples were taken at ININ and were irradiated in the reactor of the ININ, and finally the samples were measured by AMS. At ININ, 3 samples were irradiated in 3 gamma-3 with neutrons with an energy of 25 millielectron volts, a speed of 2200 meters per second, and a flux of 4.42 per 10 to 12 neutron per centimeter square per second. Different times were used for the R1 sample. Was irradiated during 30 minutes, R2 for 120 minutes, and R3 also as R1 30 minutes. The blank is our original sample and not irradiated. At LEMA, per sample, 5 aliquots were taken and pressed in cathodes. Every cathode was measured in 12 sequences divided in 10 steps with 30 seconds per step. In total is 120 steps per cathode, corresponding 1 hour per cathode, 5 samples, 5 aliquots, so 5 hours per sample. In this graphic, I represented the step. This is for 1 cathode, so they are 120 steps against the ratio that was measured in every step in atom. You can see all of the concentration of all the concentration are the concentration of every step is so constant each other, and the uncertainty is approximately 5% per step. They are the spectres. We can see the high production of beryllium-10 in the reaction, and we can compare both spectra, and we can see that for the original sample, this doesn't have beryllium-10, and here we have a big peak. So in this table shows the results for all the sample. This is the ratio atom-atom, the atom produced, and the concentration in atoms per grain of beryllium-9 that is our target. Comparing the results with the original sample, we see that these results are in 4 or 5 order of magnitude higher than the original sample. So we can say that the nuclear reaction was successfully carried out, and after this data have been used to the measurement of the Newton thermal capture cross-section on beryllium-9. So the experiment was so successful. As feature, a resin test is carrying out at this moment in our lab to determine the amount of beryllium lost in resins. For this test, several carrier samples will pass through different resins. They are the resin of our radiochemical procedure, feed resin and unit resin to remove beryllium. Second, contains resin to separate beryllium and aluminum, and third resin is other cationic resin to remove titanium and purify the beryllium. The test consists in the comparison between the current original of pure carrier, is our original sample, and the carrier after the resins. When that difference in the current, we can determine the amount of beryllium-10 lost in every resin. Also, new samples will be analyzed at LEMA, beryllium-10 in rainwater waters, to determine the production beryllium of meteoric beryllium-10 in atmosphere, beryllium-10 in ice to determine the solar activity, beryllium-10 in quartz to determine the surface exposure dating in rocks and production of beryllium-10 on Earth's surface. And finally, as a review, the optimization of the measurement of beryllium-10 in the IMS at LEMA has been carried out with the standards of obtaining a great linearity. Beryllium-10 has been measured in aerosol filters. The radiochemical procedure has successfully been adapted in our laboratory. Results obtained totally agree with those obtained by other studies and at different latitude and altitude. So our radiochemical procedure and optimization are correct, are right. The first test on the determination of beryllium-10 in volcanic rocks have been carried out. Beryllium was lost in radiochemical procedure, but good news, good spectra were obtained. The production of beryllium-10 for beryllium-9 by the nuclear reaction has been carried out in IN, and the beryllium-10 was determined at LEMA. The data show that the reaction was successfully produced with a high production rate of beryllium-10. This data have been used to the measurement of the Newton thermal capture cross-section on beryllium-9. Several tests are being carried out to determine the amount of beryllium-10 lost after passing through the resin and in the radiochemical procedure. The beryllium-10 in samples such as rainwaters, ice and quartz will be analyzed in the future. Therefore, we can say that the new research line has been opened at LEMA with beryllium-10. Thank you for your attention.
Thank you very much, Sandy. Do you have questions?
Good. Okay, thank you, Santiago, very much. In one of the maps that you show, on several of the maps that you show in two-dimensional maps, where you have this identification of beryllium-10, in the one of the last ones where you have that one, for instance, there you have a very large production of beryllium-10. And this is an opportunity to well define the region of interest that you are integrating. Apparently, you're missing some beryllium-10s outside of the region that you define. This is one thing. And the other thing is that it will be very important to identify the contaminants. You can see that there are sites like lines that go diagonal from boron and from beryllium-10. So this would be a way of cleaning the measurement and make sure that the numbers that you get are correct. Have you an idea of what are these contaminants in the maps?
Well, this is boron-10, and this is a pileup. They are particles who are reach the detector with the same energy than as the beryllium-10, but they have other mass. For example, when the beam is passing through the stripper, the beam is opened, and this particle can crash with the wall of the beam line and take the same energy than our particle. But when entry in the detector, the mass is different, so the powerful stop is different. So the specter put those particles in this zone. So those particles, you say that is beryllium-10, maybe they have a little difference in the energy, but our criteria is that with the standard is a so pure sample of beryllium with a so pure so pure ratio, beryllium-10, beryllium-9, and we make that the ROI depending of the standard. So the particles are not in this ROI. I think it's not beryllium. For me,
Okay.
Well, there is some kind of criteria that you are using there, and this is acceptable considering that you are using the standard. But it could be true that you can have some other beryllium there outside of the window of the region of integration, considering that it's very, very close to the other, to the main dot that you have there, the main region. And what could be that you have a lot of beryllium there, and the production in by means of the detection in the gas, that the events that you are detecting in the gas is huge, and then in some moment it's not well integrated in the gate, and they produce a bit shift of the particle. It could be there. But then
maybe entry very perpendicular to the window.
It lost a bit of energy.
Maybe.
Is electronica or is physical? Could be, but I'm almost pretty sure that has to be beryllium. And the other thing is curious because it appears in all the other spectrum, in all the other spectra, and then it's very similar to the tail of the boron-10. So it could be also electrical reflection of the same events, some kind of pileup. So just it has to be careful because it could be also some kind of contamination, not just in boron-10 but also in the beryllium. It should be it, but this kind of events doesn't appear when you have the standard, right?
The pileup is not usually appearing.
Thanks.
Well,
I would like to understand a little bit better what was the concrete application of the data that you applied to volcanic rocks. I mean, which was the problem to be solved with that analysis, and which are the ultimate conclusions? I mean, in geological, environmental terms. What did we learn from that data?
Okay. So you can see that the beryllium is present in atmosphere, deposited here, and after transported and gone out from the volcano. No? If we take a sample from here and after from here, the beryllium-10 in this point, this beryllium-10 we can use to calculate the time that the beryllium-10 spent during all the process.
Okay.
And we can know also the moment, we can date the moment that the volcano was in eruption.
So, which is the range of application for beryllium in dating stuff in archaeology, rocks in archaeology? I mean, for example, the people who dated the Chauvet cave in France, they obtained amazing results using chlorine. And they dated the moment when the mouth of the cave was buried by the collapse. But that was with chlorine. So in the case of
archaeologists?
Yes. So which are the applications? Because we are hungry for this kind of applications, for example, for petroglyphs, for mortars in stone, this kind of differential surfaces on rocks for cosmogenic nucleides, for aluminum.
Yes, normally beryllium-10 in situ used to date in rocks on surface and to know the production.
Would beryllium work for that, or it has to be with the other isotopes?
What?
Is beryllium useful for these applications?
Yes.
Or it goes only for geological applications?
Normally it's for geological application, but if you take rocks, normally quartz rocks from a cave, and there is bones, for example, you can compare both the dating, maybe help you.
And which is the youngest and the oldest you can date with this? I mean, the radiocarbon has the 50,000 years.
Normally it's for geological events.
So which is the youngest you can date with this one?
The youngest dating, maybe 10 million of years.
No, the youngest.
1,000.
1,000
years.
And which is the resolution you can get? How fine is the resolution?
Normally, the datation of rocks with beryllium-10 is together aluminum-26 to increase the precision with the datation.
So if I wanted to date a petroglyph, what would I use? Well, yeah, you take a sample. But
It's 2, 3, 5, 10, as you wish, kilos. After I have to pretreat me the sample to extract the quartz or the cleaner quartz. So after I need 30 grains of pure quartz to can extract the beryllium. So from imagine from half kilo, I can, depending of the quartz in the sample, of the amount of quartz in the sample. Maybe half kilo, I can use 10 grams. But I need 30 grams to get to be upper the detection limits of the machine. At least 30 grams. So if you want to bring me rocks, bring me a lot of.
So it's not ready yet for archaeological applications, right? Yeah.
Thank you. I just want to try to answer the Cyprian's question.
Oh.
It's just with cosmogenic nuclides in rocks, what you would be dating is the time when the rock got exposed to the cosmic radiation. And if you are interested in the petroglyphs, then you would be interested in a different event. Because if you manage to date how long has been this rock exposed to the cosmic radiation, it's not the same event as when a human draws something on the rock. So you would be dating the rock, not the glyph.
They are doing these experiments now using chlorine with mortars, and they are trying to get thickness, age, using isotopes.
Yeah,
The part that is not carved and the part that is carved. And they are charging $2,500 per sample, so they must be doing something with it. So
Yeah.
they are also experimenting with petroglyphs in the same way. Of course, they cannot tell if that petroglyph was sheltered from cosmic radiation at some point. That's not possible. But they are also experimenting with rocks that are, flake rocks in the Saudi desert, which were always exposed to the sun. There was never a forest there or anything. And they are from the Middle Paleolithic. So they've always been exposed to the sun for all this time. So they want to see the difference between the cortex of the original rock and the scar of the flake. So these are and the resolution there is supposed to be less than 1,000 years of precision. Now, I don't know. It seems that archaeology is trying to find a useful field in cosmogenic nuclides, but I don't know how far the technique is today in order to rely on the results, right? Because we need precision below 1,000 years, especially if you're closer in time to us. There's no point to try to date a petroglyph which is 800 years old, of course, which is the case of Mexico. Most petroglyphs are from the last 1,000 years. But probably there is a petroglyph there that you can chop into kilos of samples for the sake of science. I don't know what Ina would say about that.
More questions? Well, thank you, Santi.
Okay, thank you. Thank you.
Our next talk is analysis of carbon-14 concentration in teeth from Mexican population, and it will be given by Yvette Hill from the Forensic Science faculty.
no entiendes esto. Ay, qué complicado esto. No me queda. Sí. Okay. Thank you. You can hear? Yes. Okay, thank you so much. And also thank you for the invitation, Corina, for this workshop. So I'm going to talk about analysis of carbon-14 concentration in teeth from Mexican population. So I will try to be briefly, because right now we should be in lunchtime, so hopefully I don't spend much time. So the title doesn't specify that this topic is in forensic field, but our objective is application in forensic cases. So during the morning, we have heard about different application and methods of AMS, very interesting, all of them. So I will show you these papers in 2012. They published these papers in AMS, and I will show you these papers in methods and by other hands in applications. So please pay attention in this forensic and authentication field. For this year, they have less than 10 papers. So, and this is very important in some countries, especially in Mexico. So, what is exactly forensic? I mean, here, I like the idea, Cyprian's idea about archaeology and science are two different words. I think forensic is almost the same because this is forensic science. As you can see here, is made of different disciplines, and some of them are not real sciences, are disciplines that helps in this field. So what about odontology? I'm going to talk exactly about this area, and I can say that it's the most important area. No, it's not true. I mean, I will let you the importance of this odontology or forensic dentistry. The Interpol defines that forensic dentistry is one of the most important areas, together with genetic or DNA analysis and fingerprint analysis. So why forensic dentistry is useful to some roles? I will let you know the main roles of this forensic dentistry. The first one is human identification in living and dead people, not just dead people. So how is that possible? Because we can compare some characteristics of teeth, I mean size, form, color, and we will know exactly who is this from this teeth. The second role is bite marks analysis. We can compare the patterns, position, and we can say who is this from. And the third role is professional responsibility. This is more legal. I mean, we can say injuries, classification, and the last one, and I think the most important, is estimation. We call biological profile because we can estimate sex, age, ancestry, and sometimes, depending on conditions, we can estimate age from teeth. So just pay attention in this biological profile. When we have just teeth, I mean we don't have information to make a match. We can study this some metric characteristics or morphological characteristics, and we can estimate this sex, ancestry, age. But today, I will talk just about age. How can we estimate age from teeth? So the estimation age depends. If we have, did you remember when you change your dentition? If you have mixed dentition, we are talking about sub-adults. So this is a little bit easy because we can calculate the chronological eruption of permanent dentition or deciduous dentition or primary. So I know in this room we have some odontologists, and we can estimate, we will know exactly, or not exactly, I mean we can say a range between 1 or 2 years, and we can say that this boy or girl, this child is around, I think, 7 years. So this is good. We can do this in forensic dentistry. But what happens when we have one of these? This guy doesn't have mixed dentition, just we have permanent. And someone here can calculate the age. I mean, we can say this person has some treatments. We can see the bone, but I cannot say exactly if it's 20, 30, 40, or 50. So the methods for adults, it depends on physiological analysis. What does it mean? Here I write some methods, the most commonly used in forensic dentistry. This is through physiological wear teeth, but just look this 4 plus minus years. What about this root transparency? Look, this is 10, 8, 6 plus minus years. This is the range of estimation. And the last one is another method, and it has 5 years. So this is the first one. This is the method of wear teeth. So sometimes we can analyze how much is wear the teeth, and we can calculate, but it depends on many conditions. What if this person is, has a pathology or a stress or something else? I don't know. So the estimation is complicated sometimes. This is the second method about root transparency, and the third one is we have to calculate the area from pulp, and depends of the relation with the root. You have to calculate, and you can get this range for age. So this is the methods that we are using now. But some years lately has been reported AMS technique through analysis of carbon-14, and look at this. The range estimation is 1.5 plus minus year. So how is that possible? In previous talks, they explained very good well, so that the analysis, this strategy is based on the incorporation of C14 into tissues, in this case teeth, and showing a drastic increase in atmospheric levels after nuclear test bomb pulse. Look at this. After 1955, the curve increase. So we can calculate every year the decay of the curve, and we can know exactly the year. So it sounds very easy when we analyze teeth, but how is that possible in teeth? Teeth are one of the best body indexes for recording information about a person in forensic investigation, because teeth are the hardest part of the human body and can survive natural decay or artificial chemical treatment. So, as you know, or maybe some of you doesn't know, but enamel is the hardest tissue in our body. So it led this tissue to preserve in our body. So the dentin, it has also the same mineral that is hydroxyapatite, but the percent of enamel is highest. I mean, it's 95% of hydroxyapatite and 5% of organic matrix, this one. About dentin is 70% of hydroxyapatite and 30% of organic matrix. So I'm explaining this because in our study we are analyzing these two tissues. So nuclear techniques have been an option for forensic field in different countries. Some laboratories around the world that have contribution to solution of forensic cases. But what happened in Mexico? In Mexico, before 2013, we doesn't have this. But after this year, after LEMA, in Mexico now it's possible to perform C14 dating with this lab. So the LEMA's group has been the leader in this technique in Mexico. So we made the plan, and around C14, but this project is a multidisciplinary project, right? So we have the physical-chemical analysis. So also we have to take care about technical aspects. And in my field, biological and odontology aspects. And everything is to focus in forensic application. So we are working on it, but we have, when we made the plan, we defined three factors that we have to be very careful. The first one is the distribution of C14, because previously some authors defined 4 zones. So the regional differentiation is a result of atmospheric circulation patterns that influenced the diffusion of high C14 concentration. So it's not the same if we are analyzing a sample from someone or from Mexico. So the first thing that we have to do is calibrate this curve. So I will show you this figure because I would like to see before 1950 there are differences in each zone. After this year is very similar, right? So the second aspect that we have to check is formation teeth, because we are analyzing teeth, but in 1960, Nola described 10 stages for each teeth. So if we are analyzing enamel, look at this is first, but it ends maybe in 6th stage. So this is very important because in permanent enamel formation that begins in stage 3 and continues until 6, how many years can pass through finish the formation? So look at this table. This, the differentiation between upper and lower. So the difference in the incorporate atmospheric C14 value in the chrome versus the cervix enamel formation may thus be up to 6 years. So this is very important when we are analyzing our samples. So we have at least 28 options and different periods of formation. So the third factor is which tissue we will analyze. So the first is enamel. So we analyze the mineral, and the second one is dentin, and we analyze collagen. Because if you remember, I told before that dentin has 30% of matrix, organic matrix. So this is the difference between these tissues. This is enamel, and this is dentin. So the methodology that we designed in this study, first, maybe it sounds obvious, but the first thing that we have to do is to get the teeth. It was by donation from adults, was born after 1950s. And then this is the 3 aspects that I mentioned before. So calibration, formation teeth in crown, and tissues, collagen and mineral from dentin and enamel. Okay, this is the preliminary results. For this technique, we dissect the teeth, and from crown we separate enamel and dentin, and this is the result. This is the sample. This is the same sample, but this is enamel and this is collagen. So we we report the mass before and after the process, and also the yield from enamel. And from collagen, the same. This is the mass before, after, and the yield from collagen. This is, for us, one of the critical points, because the process is different, and we will know which one should be better for our study. I mean, if we want to apply in real cases, we have to know exactly what is the yield from each tissue. So then, this is the age calculated for individual born before 1950. This is the real year of birth, and this is the year of birth estimated by carbon-14. So before 1950, we have high uncertainties, so we just report before 1950s. But look at this, for people born between 1950 and 2002, show it above the resolution. Look at this is the year, the real year, and this is the year estimated by carbon-14. So as a summary, this is a graphical summary. I mean, this is the first thing that we have to do, the calibration for our sun, for our country. Then the processing samples from enamel and dentin, analyzing in the AMS, and then results interpretation. But from this data that I showed you before, we can conclude that although the results show that collagen and enamel age have a good correspondence to those predicted from the tooth formation date, more samples and experimental data accurately need to be considered before real cases. We need more data, we need more analysis, So we are focused on performing AMS in teeth, and some authors report the methodology. I think we are here, we are in measure, but also we have to pay attention and work and measure more samples from the same tissues. We need to study the 32 teeth just to have that data, because if we have all of them, we can compare. I mean, in real cases, we cannot say, oh, this is the second molar, so we don't have data for this. So we have to accurate for each one, and then we need to study the teeth in different conditions. What does it mean? I think Dr. Miguel Angel is working now in analysis in teeth under high temperature. What happens if we can have data about carbon-14? These are teeth. I think you have heard about this case. It's the case that has 4 years ago, and this is just teeth, no bones, no something else. So we have to study and we have to get information, if it's possible to do this analysis, to give at least the age of these tissues. So we need to study all possibilities to generate a new skill in forensic field, but exactly for our country, because I mean, there are papers, and in other countries they have this technique, and it's very possible to study in real cases, but in our country it's not really. And it can help to find missing person. Just to finish, I like this sentence because this author, Rachel Good, says that AMS analysis for forensic application is like taking the past into the future. So I think this is true. If we can go to the past, maybe we could know the year of birth of a person, and it can help to find someone who has been lost of a family. It's very sad. We have thousands of missing persons, and we have a real problems in forensic field. So we have to work on it. It's a necessity. So finally, this is the list of co-workers. As someone mentioned before, this technique is very expensive, so we got the financial support from Red Temática de Ciencias Forenses, and I would like to thank everyone here, especially the students, very smart students that had worked in this project. And of course, thanks all of you. And if you have some donation, not just it, or if you want to do an investment, just let me know. Thank you so much.
Thank you, Beth. Do you have any question?
Donations. Some questions.
So in the plot, you showed a table where you have the age of birth of the person, and then you show the C14 in the dentine and the enamel. And so you have to know, because the different teeth are going at different times, you have to know which tooth is, do you have to know exactly that it's the second molar and not the wisdom tooth or something like?
Yes.
Can you tell, you can tell this by the form of the tooth, I guess.
And this here.
Yeah.
Yes, we have to know exactly the year of birth. I mean, for example, in my case, I'm from, I will say my age, 1977. So if you want to study my incisor lower, that is the first teeth that were erupted.
Yeah.
So you need to calculate when this teeth was formed. I think here is much better. Lower, central, incisor, and you have to calculate the enamel formation, and then this is the time between 6 and 7 years is eruption, and then the root formation is after 4 years almost, or 5 years. So when we are analyzing, we have to calculate this to get the accurate estimation.
Thank you.
Other question? Well, thank you, Beth. Thank you very much.
You so
And we have finished the session. We can go to have lunch, and we come back at 3 p.m. To continue. Thank you.
Ay, me tocó regalar. Ay, déjame desconecto. ¿Cómo le hago? Yo aquí ventaneando mi